Hi guys, welcome back to the channel. In this video we are going to discuss the Johnson counter, or it is also called the twisted ring counter, or we can call it as switch tail ring counter. So let's get started. In the previous video we have already covered the ring counter. So a small change in the ring counter that makes our Johnson counter. So in the ring counter that states that number of flip-flops is equals to number of states, and two important points. In the first flip-flop we have connected the overriding input to the preset bar, first one, and the last one connection we have connected Q3 directly to the D0. So in the Johnson counter we are going to connect Q3 bar, not Q3. So this is the Johnson counter or twisted ring counter. Why it is known as twisted ring counter? Because we are twisting the ring counter. So that is the thing. So twisting means nothing but here we are connecting Q3 bar instead of connecting Q3 to the first flip-flop D0. And also for the first flip-flop we are not connecting preset, we are just connecting clear. So for all the flip-flops we have since clear, so we can overriding input as clear. So these are the changes that we have to make for the Johnson counter. Remaining all things would be same. So if you consider the number of states in the Johnson counter, so the number of states is equals to twice the number of flip-flops. So in this case we have 4 flip-flops. So in this Johnson counter we are going to have total number of states are 8. Now we are going to construct the truth table with the help of the circuit diagram also. So if you observe, first of all we are going to start our clear. So clear resets our all flip-flops to 0, whatever may be the clock. So if you observe, all the flip-flops outputs are 0, that is Q0, Q1, Q2, Q3 are zeros. So if you see, observe the Q3 bar. So the Q3 bar is given feedback to D0. In the next step, in the D0 we are going to have the Q3 bar, that is 1. So with this reason only we can eliminate the situation, that is this condition in the ring counter. The same case in the ring counter we cannot eliminate that situation, because in the ring counter all the zeros means we cannot do anything. So at least one should be there. So that is the reason the Johnson counter is used majority of the times. Now we are going to consider the next state, that the Q3 bar is given feedback to the D0 and the previous outputs are given as a input to the next states, next flip-flops. If you observe in the truth table also I have changed. Again the states are 0, and when the clock is negative edge triggered, when the clock pulse is applied at a time to all flip-flops. We already know about D flip-flop. Whatever the input comes, that only the output in the D flip-flop. So in the next state if you observe, the D0 becomes Q0, that is 1 only. So if you see, we have observed is like slight movement of zeros towards the right side, and the next state the Q3 bar becomes our 1. So in the next state we are going to take out the Q3 bar as the D0, and the Q1 means Q0 will be D1, like that it shifts to the rightwards, all outputs are. The next step, if you observe in the truth table, the red one is shifted. For your easy understanding, I have represented 3 ones in the 3 different colors so that you can understand far much clear. So you can see how the shifting of 1 happens, and how the zeros are decreasing at first. So in the Q3 bar we again have 1, so take 1 as feedback to the D0. So move all slightly to the next flip-flops, the ones. So the next thing you can observe over in the truth table. So this is the last case, that all the outputs are 1s. So if you consider the last Q3 red one, so that moves to Q3, the red one, and Q3 bar becomes our 0. So the Q3 bar again given to the D0, and again 0 starts coming up and 1 starts decreasing. So you can see that we have given a feedback of Q3 bar, that how the Q0 appears 0 and the 1s shifting to the rightward again. So you can see again we are getting Q3 bar as 0, and again we are moving all the ones to the right side, to the right flip-flops. So this is the thing, that we are going to move the things from left to right, and we are going to adjust or decrease or diminish the ones, and we are going to come back all the zeros. Again the first state. I hope you can do the remaining 2 things. So you can see that in the last case, that again we are going to have all the outputs Q0, Q1, Q2, Q3 as 0, 0, 0. So finally we are again getting the same first state. So this is the thing, that in the Johnson counter, without having one preset, all the asynchronous inputs are clear only, we can have the true state, and the number of states are extra, that is 2 into number of flip-flops. So that is an advantage in the Johnson counter. So if you observe, this is the timing diagram analysis for the Johnson counter. So as clock is, you seen that total 8 pulses are there, and the clear input is just down at once, and first remaining all things are high. So Q naught is, if you see that, raised, and Q1 is raised after a level, Q2 is corresponding to the next clock, Q3 is corresponding to the next clock, like that. With the timing diagram analysis also we can verify our things. And these are the some applications of the Johnson counter: the frequency division, finite state mission, generating timing sequence, generating one hot codes, approximation sine waves. So these are the some examples of applications of Johnson counter. So there are many applications, I put in some applications only. I hope you understood this video. Thanks for watching up to now.